You guys, any more questions?
Any of those problems are gonna show up on the exam.
Probably representative of what you're seeing on homework.
So I'll make up.
Yeah.
Thank you.
Sure. Any questions on any of those questions? No? Okay. Alright, let's continue then. So today we're gonna start with chapter 10. Chapter 10 is on correlation. So throughout the semester so far, you've seen statistics of one variable, meaning that you've seen all these numbers, but those numbers represented values of one single variable, like whether it be heights of men or IQ scores or whatnot, all those values were values of a single variable. So today we'll start talking about statistics in two variables. So we're interested in knowing if there's a relationship between two variables. So in the beginning of the semester, we talked about the difference between correlation and causation. We said that if you have two variables and they associate with each other, they relate to each other, then that's correlation. But if one is actually causes or induces or affects the other, then that would be causation. So we'll talk about whether you can look at values of two variables and tell whether there's correlation, tell whether there's some association between the two. So let's look at an example. So let's say that you look at two particular variables, and let's say you're interested in knowing whether or not, well, you're interested in looking at two variables, which is your height up a mountain and the temperature at that height. So would you think there's an association between those two variables? Like if you move up the mountain, does the temperature reliably get cooler or hotter?
Cooler.
Yeah, it reliably gets cooler. So as you go up the mountain, the temperature reliably goes down. So because of that, there's a reliable relationship between the two variables. So you would think that there should be some association or correlation between those two variables. In that case, it's straightforward, but sometimes it's much more subtle than that. So in those other times, we would want to visualize the relationship between values of those variables. So one thing we could do is plot a graph of those two variables, and that graph of the two variables we call a scatter plot. So if we're interested in the relationship between height of a mountain versus temperature, usually there's one variable that we're interested in making a prediction about based on the other variable. So it depends really on your application. But do you think it would be more natural, or you would be more interested in predicting temperature based on height or height based on temperature?
Temperature next change.
Yeah, so again, it depends on your application. Some applications you might want to predict height, the other application you might want to predict temperature. But let's say that you're moving up the mountain and you want to know what the temperature is at that particular point in the mountain. So let's say you're interested in predicting temperature. So this you want to predict based on the other variable. So the thing that you want to predict, we call the dependent variable. So this should sound familiar from algebra. So the dependent variable goes on the y-axis, so this will be the y variable. And the other variable, the x variable, will be the independent variable. In this case, it will be height. Dependent And for the scatter plot, we're just gonna plot a bunch of data points that we've observed. So let's say that we happen to observe some data points. Let's say that we have a certain height up the mountain. Let's say this is measured in meters. And the temperature, let's say we measured in Celsius.
Congratulations, we're now in Europe.
Yeah, in the rest of the world. Okay, so let's say that the height, we're at 5217 meters, and let's say the temperature is -10. So that's one data point that we have. Let's say another data point that we have is, we're at, well, let's say this is 5817. And the other data point is 2842, and that's at 15 degrees Celsius. Other data point is 2219. I'm just making up these numbers, by the way. And let's say the temperature is let's say 20 degrees Celsius. And then we're at 1,000 meters, 1,004 meters, and let's say the temperature is 10 degrees Celsius. And then we're at 7 meters, temperature is 28 degrees Celsius. And finally, we're at 4 meters, temperature is 29 degrees Celsius. Let's say this one at 10 degrees Celsius, let's make that 25. So those are the data points you actually observe. And for each data point, you could plot it on the scatter plot. So you would pick, let's label this axis. Let's say. Alright, so for each data point, we're just going to label it on this graph. So 5817 will be around here, at -10, here. And then okay, so let's say we have the scatter plot. So this is data that we observe. One is in the form of a table of points, and one is in the form of a scatter plot. So we know intuitively that there should be an association or a correlation between these two variables, because as x or height increases, temperature also changes reliably. It either goes up or down reliably. So in this case, it goes down reliably. So because there's a reliable relationship, we say that there is correlation. But if both variables move together, we call that positive correlation. If both variables, one moves up while the other moves down, then that's negative correlation. So in this case, we have negative correlation because as x increases, y is decreasing. So in this case, we have a negative correlation. So in this case, it was obvious to us that there should be some kind of correlation, specifically negative correlation. But we also want some way to quantify that with all kinds of data that is sometimes much more subtle than this. So one way that we can quantify whether there's correlation between values of two variables is we can try to measure it with what we call the linear correlation coefficient. So you notice that when we say there's negative correlation between the two variables, we're just saying that as one increases, the other decreases. So it could look like this, like in the original scatter plot. In this case, it's possible that we fit you can see that the points, you can fit a pretty good straight line through the points. And that's one kind of correlation, but also, negative correlation in general could mean that as x increases, y is just decreasing. So in this case, we can't necessarily fit a straight line through these points, but it's still negative correlation, because as x is increasing, y is also decreasing. So this is negative correlation as well, but you can't fit a good straight line through these points. But one way that we try to quantify correlation is we first ask, can we fit a straight line through the points? So we're first trying to measure correlation in general by fitting a very specific straight line through the points, and we call that linear correlation. And so if you look at your textbook, there's actually a formula for correlation, or linear correlation, and the symbol is R. And again, the linear correlation coefficient measures, imagine fitting the best straight line through these points. How good of a straight line is those points to begin with? So let's talk about the linear correlation coefficient. So if you have let's say that you have data points, and it turns out that you can fit a perfect straight line through the points. So the best straight line that you can fit turns out to be a perfect straight line that goes through every single point. So first of all, this straight line that you can fit through the points, would this be positive correlation or negative correlation?
Positive.
Positive, okay. So as x goes up, y is going up. So, because it's positive, R, the linear correlation coefficient, will have a positive sign. And if it goes through all the points perfectly, then we say the linear correlation coefficient is 1.8. So this is the case where if you have a straight line that goes through, again, all the points exactly. But in this case, you have negative correlation or positive correlation?
In this case, you have negative.
Yeah, in this case, you have negative correlation because as x increases, y is decreasing. So R will be negative in this case, but again, because it goes through the line of best fit, goes through all the points perfectly, again, the value of R will be 1.8. But it will be negative inside. So we say on the left, this has perfect positive linear correlation. And on the right, we have perfect negative linear correlation. And then let's say you had something like this. So as x goes up, is y going up or down reliably? Yeah, neither. So as x is increasing, y is going everywhere. So we say that this has no linear correlation, or the r, the linear correlation coefficient, will be 0. So all linear correlation coefficients have a value that's measured by the symbol r, and r varies. The smallest possible r that you can have is -1, and the biggest possible r you can have is 1, that reflects perfect correlation in both cases. And then anything in between represents possible linear correlation that's not the perfect case. So for example, so if you have this point here, or this line here, you notice that you have these points in your scatter plot, and then you try to fit the best possible line that goes through as many points as possible. But you notice that there's some points that still don't go through your line of best fit. So let's try to estimate what r might be. So first of all, is r going to be 1.0? No, 1.0 represents perfect fit through all the points. So first of all, is it going to have a negative sign or a positive sign? Yeah, positive sign, because if anything, the line is positive slope, or the association between the values has a positive correlation. As x increases, y is increasing. So this is positive. And we know that 1.0 is perfect fit through all the points, and this has some points it's not fitting, so this will be close to 1, but not quite. So as an approximation, this might be like 0.92. Okay, so the closer r is to 1, the better the line is best. Any questions? Okay, so let's go back to this example data set that we have of height up the mountain versus temperature. So we look at the scatter plot, and we visualize if we were trying to fit the best possible line through the points, how good is that line? I.e., what would the r value be? So it turns out that there's a formula to r. You go ahead and write the formula out. So I don't even know the formula by heart, and I'll tell you a little bit why.
Yeah, wow. Value.
Okay. It's easier for me just to hold it up. My hands are dirty.
It's textbook. It's one time you pick it up from the bottom. That's good. Page 463.
Yeah, if you notice, my book is 463. Okay, so R. Okay, so this is how you would manually calculate R, the linear correlation coefficient. I just want to talk about it briefly, but the punchline is that I don't expect you to use this formula to calculate R by hand. Ultimately, I expect you to just use your calculator, where you can just enter these two columns of numbers, and your calculator will internally use this formula to calculate R for you. But just to get a sense of what this formula is doing, so you notice that there's a bunch of sigmas here, which represent summations. So if you look at n here, that's the sample size in terms of the number of pairs of data points. So in this case, what would n be?
6.
Yeah, so there's 6 pairs of data points here. So n would be 6 in this case. And then the next summation is you want to sum up all x times y. So what this means is you would take the product, x times y in each case, and then you would sum all those up. So you would multiply each row together, 5817 times -10, and then add that to the product of the next row, and then add that to the product of the next row, and so forth. So that represents the summation, and then you subtract the summation of just the x's times the summation of just the y's. So then you would subtract out the multiplication, or the summation of just the x's, so add up all these other x's together, get a number, and then multiply that result by adding up all the y's together. So that would represent these summations up here. And then you would divide by the square root of n, the sample size 6. This is the summation of x squared. So then for each x, you would square it, and then you would add it to the next x squared. And then add it to the next x squared, add it to this squared, add it to this squared, add it to this squared. So that would represent the sum of x squared. And then this was minus the sum of all x's first to get a number, and then square the result. So notice these two are different, even though they were kind of similar. So this one is add up all the x's first, get a number, and then square the result. And then likewise for the y's over here. So the point is that if you're doing this by hand, this is extremely tedious. Any questions so far? But that tedious formula is what's involved in calculating this R value, which measures how good of a fit the line of best fit actually is. Okay, so now what I want you to do is, if you have your calculator, go ahead and take your calculator out, and every calculator is a little bit different, so I'll walk around and try to help you specifically with your calculator. But on most calculators, ultimately you want to enter in, so this will be 2 variable statistics, and then you want to enter in all your x's along with the corresponding y's.
So is that just 2 separate lists, and then go into the.
Yeah, so on your calculator, it'd be 2 separate lists. On some calculators, it'll prompt you for x1, y1, x2, y2, and so forth. And at the end, you want to select the option representing R, the linear correlation coefficient. So try to find it on your own first. If you need help, raise your hand, let me know.
So it's you 2 variable statistics, x beta, y data, and frequency is still 1.
Let me see.
So I have that, maybe one of this one, get 2 variable stats, it has to be this, so I'm assuming it's.
Yep, that's right.
And calculate about 1, yeah.
Yep. Thank you.
I'm not trying to make a bunch of assumptions, I'm just like, before I
You're
jump in the wrong rabbit hole.
So go ahead and let me know what R, you got 0.98.
I got -0.3.
17.
981817851.
Okay, anybody need help getting our calculator? Okay, good, enter the data in first, yep. And then go to stat. So on your calculator, you're gonna have to go to tests, go down. Okay, so pick linear regression t-test. That's right, okay, just gotta calculate the default here. Okay, so go down, scroll down to R. Yep. Well, yours is a little bit different, I wonder why. Let's check to see if. Everybody else getting the same R value, or are you getting something just slightly off?
I'm getting something a little bit different, but.
Slightly off, okay.
Yeah. Close.
So, the input might have been slightly off from yours. Let's see.
Not big,
17. 1 second.
Correct.
Yep. Okay. So, 0867. Okay, good. So you guys should be getting this for R. Anybody have any questions using calculator? Okay, so if you don't have your calculator here, make sure that ultimately you know how to punch this in your calculator. You can always Google this for your particular model calculator. It should give you the exact keystrokes. If you have any problems or questions with that, just let me know. I'll help you. Okay, so once you get this value for R, this is actually what we expect, right? So we expect R to have a negative sign representing negative correlation. And we also expect this value to be very close to 1, because we expect the line of best fit to be a good model that fits through these lines. So it's close to 1, not quite 1. There might be a few points that are not on the line exactly. So that reflects that this isn't exactly 1. So now the question is, okay, this isn't exactly 1, but how do we know whether this is considered close enough to 1 for us to say that this is a line of good fit through these points? So remember in statistics, whenever we try to quantify whether this is good enough or close enough, we've been using a table for that. So in this case, there's a table that we can use. And the table is basically the one after the chi-square table. It should be the linear correlation table. And so, just like before, let's say that we want to make a conclusion with a certain confidence level. So let's say the confidence level I give you is 99%. So let me go ahead and project this table up since it's the first time we're looking at it. Okay, so the table that we're using is this table. It's titled Linear Correlation. It's page 564 of your book. Table A5. So if you look on the table, the first column will be N, which represents so N represents the pairs of points. Ours is 6. So we're going to go to this row that says 6. And then we'll go over to the correct column of what alpha is. So in our case, the confidence level is given at 99%. So alpha will be 1%. So we're going to go to alpha is 1%. N is 6. So then this value is 0.917. That's what we call R critical. So R critical is 0.917, and that's found through the table. Any questions?
Negative or positive doesn't really matter in this particular case because we know which direction it's going, but if you have another situation like that, is there a difference where that negative could make you reject the?
Yeah, correct. So the negative just tells you that if the line is a good fit, then whether it's positive or negative correlation, but the value of R itself is what matters. So we're comparing the value of R and ignoring the sign to
Okay.
this value. That's a good question. Okay, so note this table for N is 6. For alpha is 0.01, we have 0.917, and if alpha was less confidence, 0.05, then we have 0.811. So let's make a note of those and let's talk about it. So we found R critical to be 0.917, and this is for alpha is 0.01, and the confidence level is 99%. So this is the context of once we get R from our calculator, the negative 9.98, the sign just tells us whether there's positive or negative correlation. But the actual value for the correlation is here. So we're going to take this value and compare it to the R critical to see whether our points on our scatter plot are considered whether the line of best fit that goes through these points on our scatter plot represents a line of good fit. So what this means is that our R value needs to be at least at this value to be considered a line of good fit. So our R value is higher than that R critical, so therefore this R value that we got is considered a line of very good fit that fits through the lines well, fits through the points well. Any questions? And because ultimately our R value is higher than R critical, and we have a line of good fit, then we say that there is a linear correlation between these two variables. This is actually a very powerful statement because you notice that we only have 6 observation points. We have observed only 6 points, and yet we're able to make this definitive conclusion about these variables, temperature and height. And we can say that there is definitively linear correlation between these two variables. We don't have to look at any more sample points. We can definitively make these conclusions about these two variables as a whole. Any questions?
Are we gonna get problems where we're doing this backwards, where we have to compute based on R critical and the R factor what the confidence level actually is?
No, not necessarily, but that's not a bad idea.
Oh, wow.
No, I'm kidding. Don't all getting on my hand after class. Okay.
Because it only gives you for that particular table, your 95 and 99%. So if you're not falling within those two categories, you basically have to reject it or give a random number that you really don't know how to compute, so.
Right, yeah, I wouldn't do that to you. So I'm only gonna give you a confidence level that's in your table, either 95% or 99%. But in real life, if you need a confidence level that's apart from those, then you know that a calculator or computer technology can help you with that. But for now, we just want to be comfortable using tables. Okay, so now that we concluded that there is linear correlation between the two variables, that means that the line of best fit through these points is actually a really good line. And if you look at this possible line, say that's the line, pretend that's a straight line. Let me try again, this is being recorded. Oh yeah, yeah. Good idea. Okay. I've never used this giant ruler before. Let's see how this goes. Apparently it's not giant enough. So you notice that the line of best fit, let's say, cheat a little bit, let's say this point is right here. So the best possible line that goes through these points, you notice, doesn't actually go through many of the points, and for those that it doesn't go through, there's a little bit of distance between the points, and that's why the R value isn't perfectly 1. So now that we have this line, because it's a line of such good fit, we should be able to make predictions based on this line. So for example, if there's any point that we haven't observed in our sample, for example, let's say we wanted to know at 1800 meters, what should the corresponding temperature be? And so just by looking at this, we see that it's somewhere between 20 and 25 degrees, so it should be somewhere between. But if we have a straight line, we know from algebra that we can actually make predictions based on this line. So we're going to look at when x is 1800, say 1800 is here, and then the corresponding point on this line would be here. And then that'll allow us to make a prediction. So if we have a straight line, it turns out that we can have an equation for that straight line. So you guys happen to remember from college algebra what the equation for a straight line is? Or how we?
Y equals mx plus b.
Okay, very good. So let's review together. I know it's might have been a long time since you guys have taken algebra.
So, for linear equations, it'd be fx equals, well, f of x equals ax plus b, point slope formation would be y minus y1 equals m, brackets of x minus x1, and so intercept was, y equals mx plus b.
Okay, good. So ultimately, all those are the same equation, but let's talk about one of them, and then you can derive any of the other. So let's say that you have this straight line. Pretend it's a straight line. And when we say that we want an equation for a straight line, what we mean is that any point that's on the straight line, it turns out that there's an infinite number of points on the straight line. And so we want to capture every single point that is on the straight line in equation form. So it turns out that this is the equation for the straight line. Meaning that any point that has an x comma y value, you plug in its x value and y value for that point, and it'll end up satisfying this equation. And that's how we can compactly represent every single point that's on the straight line. So every point that's on this line, you enter in its x value and y value, it'll satisfy this equation. And vice versa, any point that's not on this straight line, like for example 0, 0, you enter it in for x and y here, it will not satisfy the equation. So this is just me giving you this equation for the straight line and explaining what it means. But let's try to come up with it together. So it turns out that every straight line, there's a little disclaimer there, except for a perfectly vertical line, but every straight line, except for a purely vertical line, will have this equation, y equals mx plus b. B is what we call the y-intercept. For the line, the y-intercept is where the line crosses the y-axis. So it turns out here, this line crosses the y-axis at y equals 4, so that would be the y-intercept here. X and y are again free variables representing points that are actually on the line. And then the only remaining constant is m here. M represents the slope. So the slope is pick any 2 points on the line, and the rise over the run between those 2 points represents the slope. And another way to say rise over the run is change in y over change in x between those 2 points. So again, pick any 2 points on this line. We'll just pick points that are conveniently labeled for us, so we know that this point happens to be 0, 4, and this point happens to be 3, 0. So once you pick those 2 points to find the slope, an easy way to think about it is pick any of the 2 points as your starting point. Let's say this is the start. And the other point, assign as the ending point. And then you ask yourself, if you're to start at the starting point, on your way to the end, what is the rise or change in y? So how much would you have to rise or fall by in order to get from the start to the end?
-4.
Yeah, you'd have to fall by 4 units, go from the start to the end. So falling 4 is the same as rising -4. So this would be -4. and once you fall by 4 or rise -4, how much would you have to run over by to get from the start to the end?
3.
Yeah, so you have to run over by, to the right 3, so going to the right is +3, going to the left is -3. So the slope will be change in y over change in x, which is -4 over +3. So the slope here is -4/3, and that's the same slope that was in the equation I originally gave. So once you have the equation for a line, any point x, y must satisfy the equation. So let's say we're interested in knowing if x were 1, what does the corresponding y value need to be? That's a point on the line. So then we're looking for this point here. So if x is 1, what would the corresponding y value be? So how would you find that?
Substitute 1 for x in the equation.
Yeah, you know that that point has to satisfy the equation and make it true. So therefore you just put in 1, and whatever y comes out that makes the equation true will be the y value. So the point is that once you have an equation for the straight line, for any point, you can find its coordinate. So same thing here. If we have a line of good fit through these variables that represent height of the mountain and temperature, once we have that line of good fit, then we can model that line and get an equation for the line. And once we get an equation for the line, we can plug in any point of interest and we can get the corresponding y value. So your calculator will be able to do this for you. So around the same areas where your r value was found, there's also one that says A and B. So these two variables, one will stand for the slope and the other will stand for the y-intercept. But it turns out that calculators are made all over the world and there's different conventions. So on your calculator, A may be the slope or A may be the y-intercept. But once you figure out the convention for your calculator, it'll be consistent. So you'll just have to figure out of the variables A and B that your calculator gives, which one is the y-intercept and which one's the slope. So go ahead and try to find that. Try to find the equation for this line of good fit that goes to the points, and I'll walk around and help if needed.
I'm gonna assume the slope is negative.
Very good. So this, you already know the slope has to be negative. So if those two numbers, if there's only one that's negative, then you know that that one's the slope. So I'm gonna label these as M and B. So what are you guys getting as your slope?
So what I have calculated on A says negative 0.00650.
Okay.
And the slope I have 30.7229.
Okay, so the rest of you guys getting these two values? Okay. anybody need help? We can do it.
It's weird though, when I put it all together to get the temperature, it's not between 20 and 25. It's
Yeah,
19.
that's because I drew it not very well.
Yeah, it just says it's like 19 degrees Celsius.
Okay. So. Let's go ahead and put it all together. So this line of best fit that goes through the points has this slope and this y-intercept. So let's put it all together. So y has to equal mx plus b, where m is negative 0.0065 and b is 30.7229. And so let's say we're interested in knowing at 1800 meters, what does the corresponding temperature need to be? What's the y value? So let's plug this in. And what y value or temperature are you getting?
19.02.
I got a 7. You have one negative.
I think it was business seven, when I wrote it down.
So what this is saying is that the best possible line that results in the minimum distance of your observed points to that line will end up predicting a value of 19 degrees in temperature to this height of 1800. So you notice that according to this data, we were trying to predict that around 1800 should be between these two, 20 and 25, but we're getting is something a little bit less. And it's because the straight line of best fit isn't trying to go through all these points perfectly. It's trying to minimize the distance between all the points. And so the best fitting line ends up not necessarily being able to interpolate between these 2 points, but it minimizes the distance between these points on the line as much as possible. Okay, any questions? All right. So let's say that we had another data set. Okay, so let's say in this data set, let's say that in your next job you're a detective and you're on a crime scene, and the only evidence that's left is shoe prints. And you wanna know whether you can use the shoe prints that you're observing to predict the height of the criminal who's left the scene. And so you wanna know whether there's an association or a correlation between shoe print size and height of the person. And so then you go to look at sample data that's completely unrelated to this crime. And let's say that your data that you're looking at is, let's say shoe prints in centimeters versus height. In centimeters. Where did Europe begin? Okay, so of these two variables, shoe print size and height, the thing that we're trying to predict is height. So we'll call that the y variable, the dependent variable, and shoe print will be x. So go ahead and enter that in your calculator, those pairs of points, and let's talk about what the R value, the linear correlation coefficient, is.
We have an R value of 0.59126.
0.59126. The rest of you guys getting that? Okay, great. Okay, so we said that if the R value is close enough to 1, then we say that the line of best fit is actually a good line. But in this case, 0.59 doesn't seem very close to 1. And we can actually quantify that more exactly by comparing this R value that we got to R critical in the chart to see whether it's actually close enough to 1 or not. And so go ahead and try that, and let's use a confidence level of 95%. So notice that the more we're willing to be less confident, the lower the R critical will be. So let's say we're willing to be 95% confident. So let's find, so alpha will be 5%. So go ahead and look up R critical.
0.878.
So if you're willing to be only 95% confident, then your R value needs to be at least 0.878 to be considered a line of good fit through the points. So in this case, it's not a line of good fit. So let's talk about what our conclusion should be. So remember, before, when our R value met the threshold of our critical, then we ended up saying that this was a line of good fit, and therefore there is correlation. That's the case where our test is at least as much as our critical. Specifically, there is linear correlation. But in this case, we have an R critical that is 0.878, and our R test is lower than that. So, based on this, our conclusion should not be that there is no linear correlation. So we should not make this conclusion. Because we've only observed these 5 pairs of points. We can't make a conclusive statement yet. Maybe we need to observe more points. Or maybe if there's no linear correlation, there could be another kind of correlation. So we can't yet make this definitive conclusion yet. So this should sound familiar from hypothesis testing, but the best conclusion we can make is we can't reject the idea that there is linear correlation. So fail to reject the idea that there is no correlation. So that means we haven't quite embraced no linear correlation yet, but we're going to lean towards that and hold on to that idea. It could be true. So we're not going to reject the idea that there is no linear correlation. And again, fail to reject doesn't mean that you can never reject the idea in the future. It just means that for now, based on the sample of 5, don't yet reject this idea that there's no linear correlation. So again, this should sound very familiar, this kind of verbiage from hypothesis testing. And later on, after we do a few examples, we'll actually formalize it in terms of hypothesis testing. So we can exactly identify where this wording is coming. Any questions? Okay. So if our test meets the threshold of our critical, there's already enough evidence for you to say that there's linear correlation. You don't have to observe any more data points. You can conclude that there's linear correlation between these 2 variables in general. If our test does not meet the threshold of our critical, then you can't just say that there's no linear correlation, but you don't reject that idea that there's no linear correlation.
So we're not going with true-false statements, so do we actually need to, start at the beginning, identify our claim, and then make your counterclaim?
Yeah, that's what we're gonna do in a moment.
Okay.
Yep. Okay, good. So right now, I just want you to get used intuitively to this phrasing, and then in a little bit, we'll talk formally in the context of hypothesis testing. How this verbiage actually matches what we've been talking about all along with hypothesis testing. Okay. So what this, our test that we've calculated implies is that the best possible line, the best possible fitting line that goes through these points is not a good fit to begin with. And so if you were asked to make a prediction, for example, based on a shoe print, what the height of the person might be, so for example, based on 30 centimeters, let's say 30.5 centimeters. Do you think that we can make that prediction simply by saying it's somewhere between 177 and 185? So we're trying to make a prediction based on the shoe print of the person being 30.5 centimeters and seeing what their height needs to be. And do you think it should be somewhere between 177 and 185?
I mean, we've got basically 60%, so I would take your highest and lowest and shoot somewhere in between there. I'd say you have better odds of saying yes or no to that if you're using 172.7 and your highest is 185.4.
Okay, good. So it turns out that in this case, we don't know what the best model is to make this prediction is. Because we tried fitting a straight line to the points, and we saw that there's no good straight line that fits to these points. And so you can't model the situation with a straight line. So your calculator is going to give you a slope and a y-intercept anyway, but do not use that slope and y-intercept to make a prediction for this. So if you're asked what the best prediction is for this value, the best really that you can do is take all these y values and find the average of those y values and just say that the best predicted value is that average of the y values. So take the average of all these observed y values, these height values, and whatever the average is the best predicted value anyway. So again, you can't make a prediction based on the line of good fit. So your calculator is going to give you an A and B anyway, but don't use those to make any predictions on because this R value is low anyway. So incidentally, the A and the B value that your calculator gives you to find the line of best fit, that line of best fit is called the regression line. So just so you know that term. So regression is just trying to find the best curve that fits through all the points in your data set. In this case, the curve that we're assuming is a straight line, so we call this a regression line. Okay, so let's put this in the context of hypothesis testing, which we've been talking a lot about past few classes. So let's use this example that we just did with shoe print, size, and corresponding height. And we're trying to decide whether there's linear correlation between these two variables. And we calculated the R value and saw that it was low in comparison to R critical. So therefore, we said intuitively that our conclusion should be, we don't reject the idea that there's no correlation. So let's formalize this with hypothesis testing. So in hypothesis testing, there's a claim we're trying to make. And the claim can either be that there is correlation or there is no correlation. It doesn't matter. But let's say that our claim is there is correlation. And then we have an observation in the form of these 5 sample data points to try to substantiate the claim. So the next step of hypothesis testing is we're going to identify the 2 statements, H2 and H1. So we'll introduce the counterclaim. Counterclaim is the opposite statement. So what's the opposite statement to?
There is no correlation.
Okay, good. There is no correlation. So before, when we saw that this case where there was no correlation, what was the R value here?
0.
Yeah, it was 0. So let's do this mathematical statement for there is no correlation. So the linear correlation coefficient for the population needs to be 0. And so notice that we introduced this variable R. That's the linear correlation coefficient for your sample of points of your variable. But remember, the hypothesis testing, the claim and counterclaim, are population statements. So if you had all your population data and took the linear correlation coefficient, then that would be this symbol for the population linear correlation coefficient, or rho. Looks like it's a Greek letter rho, it looks like a fancy P. So this is the population linear correlation coefficient. If it's true that there's no correlation, then that rho should be 0. What about if there is correlation? What should the linear correlation coefficient be? It should be close to 1, but we don't know how close to 1 is considered close enough. So we know that as long as it's distinctly far apart from 0, then that's considered correlation. So we're going to say that correlation means that as long as it's not 0.
Okay.
So rho not 0, the same way of saying that is either rho is greater than 0 or rho is less than 0. Okay, and so the next step in hypothesis testing is identify the null hypothesis.
So we're,
There is no correlation?
Yeah, so the statement that has equality would be the null hypothesis. So in this case, there is no correlation. So that will be the null hypothesis, HO. The other statement will be H1. So what we do now is we assume the null hypothesis is true for the next step. So let's look at an underlying distribution. And you remember, as with before, the name of the game was decide whether the observation is in the body or the tail. So in this case, do we have a one-tail test or a two-tail test? Yeah, two-tail, look at H1, and look at the number of inequalities. So you have a two-tail test here. And then remember the chart lays out two possible values for alpha. One is 0.01 and one is 0.05. So depending on the alpha, whether it's 0.01 or 0.05, then these values for R critical will be at those values that are in the chart. So these are critical, are the chart values. So this is from chart. And then the R value that we calculate from our calculator, we can call that our test, or the test statistic. So let's do the first case where, let's say R critical is this certain level, and then our test passes the threshold of that R critical. So that means it's in the body or the tail. Yeah, that means it's in the tail because it's above R critical. So that would be the example of this example here, where our test was 0.98, which is above our critical. So it met that threshold, and we ended up concluding that there is linear correlation. So let's see if that is consistent here. So our test is greater than our critical, so therefore it's in the tail of the distribution. If it's in the tail, that means the observation is not consistent with the idea that HO is true. So if it's not consistent, then we can do what with HO?
Reject it.
Yeah, we can reject HO, and we can accept H1. We always want to bring it back to the original claim. The claim is that there is correlation. So that claim is H1, so then we look at what we said about H1. So we're going to accept H1, or accept the claim that there is correlation. That's exactly what we said before. That if our test exceeds our critical, then we say that there is linear correlation. So another way to say that is that there is enough evidence to conclude that there is linear correlation, and we don't need any more evidence. Any questions? Okay, so that's in the first case. In the second case, our test did not exceed the threshold for our critical. So let's look at how that might look. So that means our test would be somewhere here. So in this case, your observation is in the body of the distribution. And if the observation is in the body of the distribution, then the observation is consistent with the idea that HO is true. So you have one observation that's consistent with the idea. So you can't accept that idea, but you fail to reject HO, and then fail to accept H1. In this case, we said the original claim turned out to be H1. So what we said about H1 is fail to accept H1, so we're going to fail to accept the claim. So we fail to accept the claim that there is correlation, which is another way of saying fail to reject that there is no correlation, which is what we ended up saying here. But either one will be okay. So again, you can say either fail to accept that there is correlation, or you can fail to reject there is no correlation. Any questions? So I'll write both here. This first conclusion might be more intuitive, easier to think about. Is all this means is that you can't accept immediately, based on this sample, that there is correlation. You're going to have to keep observing more things.
When it's said and done, if it still ends up in the tails, it is being rejected, and if not, it is a fail to accept or fail to reject, depending on which one you're pointing at.
Yep. If you're in the tails, it's either flat out accept or flat out reject. If you're in the body, then it's fail to accept or fail to reject. Okay, good. Any questions? Okay, we don't have not a lot of time left, so we'll just go ahead and continue next time.
Who you got?
Have a good day, guys. Thank you.
So we're doing section 10.1 and section 10.2, and then it goes into reversing intro.
Yeah, so the only thing left in chapter 10 we have left is rank correlation. I think that's 10.3 or 10.4.
And then we'll
so that's, we already did that class, so the only thing left is the last part of chapter 10. I think it's 10 to 3. Yeah, wait for it. So that's what we did for the next
Did you see in, math lab, the assignments that had been omitted or not? Saw that yet?
Oh, yeah, I've seen it, I'll correct.